Okay, 47. Birth order. A couple plans to have 3 children. There are 8 possible arrangements of girls and boys. For example, GGB means girl, girl, boy. All 8 arrangements are equally likely. You write down all 8 arrangements. Okay, try to do this as systematically as you can. Okay, girl, 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 boy, girl, boy, girl. Otherwise, it's easy to get not confused, but it just takes longer. So there's all the girls, there's one boy. Now we'll do 2 boys. Girl, boy, 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 girl, boy, 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 girl. And now we'll do 3 boys, or no girls. 1, 2, 3, 4, 5, 6, 7, 8. There's all 8. That would be the sample space. And we're going to let X, we're going to make a model here. This is the number of girls. And this is probability of X. We write this as little x for one of these values. So the number of girls, well, you could have 0 girls, 1 girl, 2 girls, or 3 girls. Okay, well, what's the probability that we're actually doing part C right now, and then we'll answer part B from this table. The probability of 0 girls would be, I wrote boy, boy, girl here. I'm sorry. That should be boy, boy, boy. 0 girls is this one right here, so it'd be 1 out of 8. 1 girl would be that one, or that one, so it'd be 3 out of 8. 2 girls, that one, or that one, 3 out of 8. And 3 girls, of course, is 1 out of 8, and you can always check yourself. These all have to add up to 1. 3, 6, 7, 8 out of 8. Okay, so we're good. So this is my distribution of X. This is my probability model. Okay, those are the different values X can take, and those are the probabilities. What's the probability that X is 2? Probability that X equals 2 is, of course, 3/8. And that's how we would write it. Alright, and let's do 51. Did you vote? Sample survey. Now we're going to start combining some things here. Contacted a SRS of 663 registered voters in Oregon shortly after the election, asked what they had voted. They show that 56% had actually voted. We'll see later that this situation represents the proportion of the sample who voted. Call this proportion V. Has approximately normal distribution with mean of 50. Okay, so we got normal. The mean is 50.56 and the standard deviation is 0.019. Before I even do the problem, I'm going to draw a picture here because it says that it's a normal distribution. Mu is 0.56, sigma is 0.019, and this is the percent of registered voters who actually voted. Okay, so that's what this tells us. Now I'm going to look at A. If the respondents have to answer truthfully, okay, what's the probability that the percent V, the percent who voted, is between 52 and 60, the actual proportion of people? Okay, so between 52 and 60. So we're looking for that. All right, probability 0.52 less than or equal to V less than or equal to 0.60. Well, how do we handle that? I'm going to go ahead and convert these to z-scores, but before I do that, let's read the rest of the question here. This is a probability that the sample proportion V estimates the population proportion 0.56 within 4%. So 0.56 plus or minus 4%, what's a probability that we're in that range? Okay, we're going to spend a lot of time talking about this in class. So I'm going to convert this to z-scores to find that probability or that proportion. So it'd be 0.52 minus 0.56 over 0.019. 0.6 minus 0.56 over 0.019. So that's my z-score of, I'm doing it right here on the side, 0.52 minus 0.56 divided by 0.019 is negative 2.1. Oops, this is no longer V, sorry, this is Z because I converted it to z-scores. So that's Z. And since it's symmetric, it's the same on both, 0.04 up and 0.04 down. This is going to be 2.1. Okay, so I'm going to look this up on the table in the back. And if I look up negative 2.1, let me find it here. Oops. Negative 2.1 is going to be, the area to the left is, this area over here is 0.0179. That means this area is 0.0179 because it's symmetric. And so that's going to be, the area in the middle is going to be 100% minus 2 times 1.79%, if I write it in percents, right? So that's going to be 100 minus 2 times 1.79, 96.42%. So that's what this is right here. So the probability that V is between, 52 and 60 is 96.42%. Okay, and B. In fact, 72% of the respondents said they voted, so it's way up here. Okay, because this is from voter records, right? 72% said they voted. If the respondents answer truthfully, what's a probability? What is that probability? Okay. So let's do this over here. How about that? What's a probability that V is greater than 0.72 or equal to? What's a probability that Z is greater than or equal to 0.72 minus 0.56 over 0.019 and 0.72 minus 0.56 divided by 0.019. Oh, I messed that up. 0.72 minus 0.56 divided by 0.019. Oh, I didn't mess it up. Probability Z is greater than 8. The z-score is just huge. 4.2, which isn't even on my table. That's going to be approximately 0. That is going to be so far. Look how many standard deviations. 8 standard deviations above, which is next to impossible. Okay. So let's take a look at what does this mean, okay, practically, because this is what where we're heading later on in the course, which is really the meat and potatoes here. If respondents answer truthfully, what's the probability that it's greater than 72? Essentially 0. There's really no chance of that happening. The probability is so small that it's good evidence that some people who did not vote claim they did vote. In other words, we know that 56% of the registered voted actually voted. So if 72% of our sample said they voted, well, our sample is going to vary, right? Because we know that 56 actually voted. I'm going to get samples where some samples 58% might vote, some 53%, some of them 60%. In fact, 96% of the samples are going to be between 52 and 60%, right? So what's the chance that I get a sample where it's 72% or greater say they vote. That's almost zero. So is it likely for me that I'm going to get a sample that large? Nope, not likely at all. So therefore, people in this sample probably lied. Okay? All right. There you have it.